I'd like to start by echoing a previous speaker. There's nothing better than seeing your former students doing well. Okay. I'm actually going to give an academic lecture. I'm not going to mention verticals or horizontals or late-stage valuations. I'm going to tell you how neural networks actually work. So, in the brain there's real neurons, and we have artificial neurons, which are gross simplifications, but they're good enough to get the job done. And so if you look on the left there, there's a little picture of an artificial neuron that has one output. It gets a bunch of inputs from other neurons, and on each input it has a weight that it can adjust. And the way it decides how much output to give is it takes the inputs from other neurons, multiplies them by those weights, gets a total sum of input, and then gives an output that's that function on the right. So if it doesn't get much input, it gives no output. If it gets enough input, it starts giving an output that's a linear function of how much input it got. That's how a neuron works. And real neurons are more complicated, but this is good enough so we can study how big collections of neurons can do things. For example, we can study how a big collection of neurons might be able to take the intensity values in an image and convert those into a string of words describing an image. We hook up these neurons into networks. The simplest kind of network is a feed-forward network, where we have multiple layers of what are called hidden neurons between the input and the output. And so you put in some activities at the input, like pixel intensities, and you get out activities of some output neurons which might represent the classes of the objects in the image. And what we'd like this network to do is to take a bunch of pixels like that, and remember that's just a million triples of numbers that describe RGB intensities, and convert it into a string of words. So I want you to think for a minute what it would be like to write the program that does that. Okay, that was painful. You've no idea how to write the program that does it, so we need to get a learning algorithm to do it for us. And so we're going to have a learning algorithm, and I'm going to explain to you the learning algorithm we don't use, because it's one you can understand, and then I'm going to explain to you that the learning algorithm we do use is just an efficient version of this one we don't use. So imagine that you took a network that took input and gave you outputs, and they weren't the outputs you wanted. And how would you make it better? Well, what you would do is you'd take a random batch of examples, you'd give it the inputs, you'd look at the outputs you got, and then you change one of the weights in the network, just one of them. And you give it the same examples again, and see if the outputs were slightly better or slightly worse. And if they were slightly better, you keep that change. And clearly, if you did that for long enough, for evolutionary time, you could eventually find a bunch of weights that did a good job. But it would be very, very slow, particularly since you've got about 10 to the 14 of these weights you need to adjust. So there's a better way to do it, which is to use calculus. And the backpropagation algorithm is just doing what I just said, but it figures out for all the weights at the same time whether you should increase them a little bit or decrease them a little bit, so that on that little batch of cases you took, the answers get better. And so you take a little batch of cases, you'll figure out for all the weights in parallel how to change them, you then change them all a little bit in the direction that makes things better, and hey, eventually the thing will learn to do good things. Now, this has been used a lot since the 1980s, and so the backpropagation algorithm takes inputs, it runs through multiple hidden layers, it gives outputs, and then you send information backwards through the network, that's the calculus bit, to figure out how to change all these weights. And the thing we hoped is that if you show it images of animals, for example, and you tell it has to classify them into birds or cats, then what it'll do is in the first layer of units, it will find things like edges. In the second layer, it'll find things like little combination of edges, maybe a beak, or maybe a little bunch of edges that form a circle. And then if it finds the right combinations of beaks and eyes, then in the third layer, it'll say bird. And this is a gross simplification, but actually this now works. You can feed it lots of images, and it will find features in the first layer that are simple features, and features in the second layer that are more complicated features, and so on, until it's found very complicated features that are enough for it to classify. So backpropagation got people very excited in the 1980s when people first started running it on workstations. It was used for things like reading the numerical amount on checks at the end of the 80s, detecting credit card fraud, interpreting pap smears. But there was a backpropagation winter. It didn't work as well as his advocates thought it should work. So people like me went around saying, this is going to solve everything. We're going to be able to do speech recognition, we're going to be able to do vision, we're going to be able to do language eventually. This is amazing, and we will solve everything by learning these layers of representation. And we couldn't. So that was the end of that. Now, between about 2000 and 2015, there have been a bunch of little technical developments, like using different kinds of neurons, ways of preventing them from fitting the quirks of the training set. But all of those aren't the main message today. The main message is this algorithm, if you give it a lot of labeled data and you give it a lot of compute power, will do amazing things. And what was wrong in the 80s was simply we didn't have enough data and we didn't have enough compute power. We have made it work better with little technical advances, but those were the main things that were wrong. So the first killer app of the recent wave of interest in deep learning was for speech recognition, where people had a lot of labeled data. And on a relatively small data set with only a few million examples, 2 students in my lab, while I was away for the summer, trained a net that was deeper than I thought you should use, and it actually had 8 layers. I could only bother to draw 4. And they showed that they could slightly beat the state of the art on this small data set. And a very intuitive researcher at Microsoft called Li Deng then realized, well, if students in my lab could beat the state of the art, real speech researchers could do a lot better. And very quickly, this same network was used at Microsoft to do big vocabulary recognition and significantly beat the state of the art. So all the leading groups then got into this technology. By 2012, it was actually being used in the Android, in the cloud, if you had the Android operating system, for doing speech recognition for voice search in Google, and it gave a big decrease in word error rate. So I think Google were the first to get it into production. And now all of the best speech recognition systems use some form of backpropagation for training. The next killer app was object recognition. So until quite recently, people tried to do object recognition with training sets that were much too small. And someone called Fei-Fei Li at Stanford put together a team, and that team labeled lots of images. And so they had millions of labeled images. And that was one of the main breakthroughs. And then 2 very smart students of mine, one of whom you will see today, got a system working by using big neural nets on this big labeled data set, and they did a lot better than the best computer vision systems, and that caused a revolution in computer vision. The revolution should have happened sooner, because someone called Jan LeCun had been saying for years, these kinds of nets can do much better than you guys. But they could only do better with enough labeled training data. And they didn't have it till Fei-Fei Li put this data set together. That's not quite true. Jan submitted papers where his network did better than the state of the art, and they were rejected by conferences, even though they admitted they did better than the state of the art, because it was a neural network, so it wouldn't teach you anything. You wouldn't be able to hand design the system based on what the neural network did, because it just learned a big bunch of numbers. So that was of no interest to computer vision. Then over a period of about a year, they completely changed their mind. And this was the beginning of the downfall of conventional computer vision. There was this competition in 2012. All the computer vision systems were getting more than 25% errors. And the net we developed at the University of Toronto, by people who weren't really doing computer vision, got 16% errors. That was a huge win, much bigger than the win we got on speech recognition. And people saw that, and they finally read the writing on the wall. I think they couldn't read the writing on the wall before because they weren't using neural nets. Now, the error rate is down to 5%. In fact, this slide is a few days old. It's now 4%. So it's amazing the progress there's been. And these are the kinds of images you can recognize. You don't have to have the whole object. It knows that's a cheetah. And its second best guesses is a leopard or a snow leopard. So its other guesses are good guesses. If you show that, even though the bullet train is only a small fraction of the image, it knows about what people tend to focus on in photographs. And so it knows that's a bullet train. And its other bets are quite good bets. For this one, its first bet is a hand glass, sorry, its first bet is scissors, and its second bet is a hand glass, and its third bet is a frying pan. If you screw your eyes up, you can see why it thought it might be a frying pan. It didn't recognise that that chain is actually not a solid handle. So basically, this system needs glasses. But you can see that they're visually similar things it's getting. And the last thing I'm going to talk about is recurrent neural networks, which are really just feed-forward neural networks in time. I'm not going to talk about the technical details required to make these work really well. You can read a paper by Hochreiter and Schmidhuber in 1997. If you can understand that paper, you're better than anybody in machine learning was. It took 10 years before people understood what they were talking about. Okay, a recurrent neural network works like this. You have inputs, like images, for example, but they arrive over time. So this would be for video, let's say. And then the hidden neurons connect to themselves. So the connections that you see with the little green and red dots are connections of hidden neurons to themselves, and they're the same at every time slice, because it's the same way it's being reused. And then at each time slice it can give outputs. You might wait for a while before you give any outputs. And we can train that with the same backpropagation algorithm. And those also we couldn't get to work well in the 80s, but more recently using Hochreiter and Schmidhuber's version, people have been able to get them to work nicely. And then Ilyas Skiva and Oriel Vinyals and Kwok Lee had a very good idea. Yoshua Benjo also had a similar idea. But I think they made it work on whole sentences first. The idea is a really dumb way to do machine translation. We're going to do machine translation not by learning which phrases in English go to which phrases in French, which is how Google Translate does it. We're going to do machine translation by listening to the first sentence, understanding what it means, and then saying it again in the other language. That's the obvious way to do machine translation. The only drawback is you have to understand what the first sentence means. And we're going to get a recurrent neural net to do that. And it's really actually going to be fairly straightforward. So what we do is we have an encoder recurrent neural net that takes a sequence of English words. At each time step you put in one word. The word gets converted into a big vector of features. That is a big set of activations of features. These feature activations then drive the hidden units. And at the next time step another word comes in. You get more feature activations. And the hidden units at the second time step are driven by the word at the second time step, plus whatever the hidden units were doing at the first time step. So in that hidden state, you're gradually accumulating information about what all the words were telling you, but in the context of what words already arrived, and you're trying to integrate that information into a single vector. By the time you get to the end of the sentence, you'll have some vector that's been influenced by all the words in the sentence, and we will declare that vector to be a thought. Now this seems very weird for people in AI, because people in AI and philosophy and logic always thought that thoughts were symbolic structures. They were sort of tree structures made of symbols or something like that. But we're going to say thoughts are just big vectors. And that's clearly what they are in your head. In your head you hear some words, and then there's some state of activation of your neurons, and that's the thought you had. Okay, so we're going to take this thought vector, and we're going to say all we need to do now is turn that thought vector into words in another language. Of course, since we start off with all random weights, it'll be some random thought that's not related to the words to begin with. But after we've trained it, it will be. And so what do we do with the thought? Well, we make that thought vector be the input to a decoder neural net. Let's suppose it's speaking French. And the first thing the decoder net says is, what do I think the first word of this sentence should be? And it has bets about the various first words. If it's doing French, it might say le 40%, la 45%, cha 5%, and I don't know any more French, but there's some other words as well. So it'll make bets across the first word. If you were to pick one of those bets and then feed it in and tell it what word you picked there, that would then change its hidden state. It would have already said that. And it would then make bets for what the second word might be. So it's unlikely to think it's le or la if you said le first. It might think it was cha. Maybe there's 30% on cha now, and some more on other French words, and so on. So if you now pick from what it says and feed words in, it'll give you a sentence. And each time you pick, if you pick differently, it'll give you different sentences. When you're training it, what you want is that when it gives you a distribution across words, when it says the next word is probably Shah, if the next word really is Shah, you say, hey, that's good, change all the weights to make that a bit more probable. So go backwards in time, looking at the pathway of weights that led to this decision, and go and change them all to make this decision a bit more probable. If Shah was the wrong word in the given translation, you go back through that pathway and change all the weights to make this a bit less probable. And that's it. You just train it like that. It starts with random weights. You train it on lots of pairs of English and French sentences. And hey presto, trained on one pair of languages, it does comparable with the state of the art on a medium-sized database. And with more recent tricks that involve attention, it does even better. And once we've trained this on lots of pairs of languages, using the same thought vectors for many different languages, so you can take an English thought vector and translate it into many different languages with different decoders for those languages, we think we'll have something that's so good that you could, for example, take encoders for many different languages, you could take a decoder just for English, you could put it all on one chip and you could stick it in your ear. That would be the hope. I hope some of you have read The Hitchhiker's Guide to the Galaxy. Okay. So I'm going to finish by showing that you can put those two bits of work together. You can take the feed-forward neural network that recognizes objects and images, and you can feed the decoder network. Instead of feeding it with the thought that comes from an English sentence, you feed it with the thought or the percept that comes from looking at an image. So you look at the image, you do lots of clever early layers with clever tricks called convolutional neural nets, which I haven't explained. That just before you get to the class labels, you just declare the activity in that last layer to be a percept. And that's a percept that you know is looking at the image and understanding it in terms of the kinds of objects that might be there. And then you map that percept to a thought, and then you decode the thought into English, using exactly the same kind of network as you use for decoding an English sentence into French, except this is the English decoder. And if you show it that image I showed you at the beginning, it will say something like a close-up of a small child holding a stuffed animal, which is a pretty good caption. It's pretty impressive for something by pure learning to have got from the intensity values of pixels to a string of English words that's appropriate. Here's another example. If you show it that, it'll say a group of people shopping at an outdoor market. If you run it again, it might say something different. The thing that you probably can't read in the light type is the correct caption, which is better. It's people crouched around in an open market. But the point is, it works. Now, this will have big implications for document processing, because with this kind of technology, we can take a sentence and convert it into a vector that's the thought behind that sentence. And if you ask what a document is, it's just a sequence of thoughts. Once you've got rid of the words, it's a sequence of thoughts. And all we have to do now is model that sequence, and we've understood documents. What's more, we've understood how people reason. We've understood natural reasoning, which is what symbolic AI could never do. They tried all sorts of fancy screw-ups of logic to try and understand natural reasoning. But actually, this is the way to understand it. Now, you might not want to understand natural reasoning, because this will be reasoning on the web, and you can't really call it reasoning. But at least you'll understand what happens when people go through a document. I have some reservations about how long it's going to be before we can really understand documents like this. And my reservations are mainly to do with how many weights we have in a brain and how many we have in these networks. In these networks, we have typically 1 billion or less of these learned parameters. In our brain, we have about 100,000 times more parameters. And it may be you need that scale of parameters to get human-level understanding. We just don't know. So I'm going to show you a test for whether we've really got close to human levels. And this is a test that these automatic translation systems cannot solve at present. It's a test designed by the good old-fashioned AI people who had to find something these neural nets couldn't do. They were getting desperate. And so they found something the neural nets couldn't do. And once the neural nets have done that, they have to give up because they chose the battleground. They said, if you can do this, we give up, essentially. And you'll know that we finally won when we can do this, but it may be a few years off. And so here's the final test. If I give you the sentence, the trophy would not fit into the suitcase because it was too big, and you ask, what does that it refer to? You know that it refers to the trophy. And you know that because big things don't fit in small things. But if I say the trophy would not fit into the suitcase because it was too small, you know the it refers to the suitcase. Okay? You do that effortlessly. You don't realize you're doing this reasoning, but you just know the way things work in the world, and you can't put bigger things inside smaller things unless you're watching Doctor Who. So the question is, do the neural net translators, do they understand this? And the point is, they don't do better than chance. And it's very easy to test this because you just translate these English sentences into French. And in French, you're not allowed to say it. You have to say either le or la. And in the first case, it's either le or la, and in the second case, it's the other one. Okay, that's the end.